I guess let's wait for 1 more minute and then we'll start. Okay, so I guess let's start. Welcome to the one of the crypto session. So the title of the first talk is Revocable Quantum Digital Signature by Tomoyuki, Alex, and Takashi. So Takashi will give a talk.
Thank you for introduction. So I'm Takashi from NTT and Kyoto University. And today I will talk about revocable quantum digital signatures. So let me start from introducing the concept of copy protection. Suppose that Alice bought some game from some company and she enjoyed the game a lot. So she wants to share the game with her friends and just copied this and distribute to her friends. And then, okay, so they play the game. And so they're happy about playing the game. But of course, the company is not happy because they're not paying for playing the game. So for preventing such a copying attack, the one way to prevent such a copy is to encode a game program into a quantum state. Then, by the no cloning theorem, Alice cannot copy the game, and so they cannot distribute the game to the friends. So they are not happy, but the company is happy because they prevent the copy. So this is a concept of quantum copy protection. So this is, for this copy protection, the no cloning theorem is essential. And a related notion is a secure leasing. So in secure leasing, the company wants to lease a game program to the user for a certain period. So when the game is leased, the user downloads this quantum program and he can play the game for a while. And at some point, when the leasing expires, the company requests her to delete the game. And then she deletes a program and generates some proof that she actually deleted the quantum state, which encodes the game. And then the company verifies this proof of deletion. And if it passes the verification, the company is convinced that the user surely deleted the game. So this is secure leasing. And I would like to remark that for secure leasing, no cloning is also essential, especially if no cloning, if the user can clone the same state, then secure leasing can be broken as follows. So suppose that the user downloads the game, and then suppose that she can somehow clone the same state. Then she can just use one of the copies to generate the proof of deletion. Then company is convinced that she actually deleted the game, but actually she still has another copy of the game. So for achieving the goal of secure leasing, again, the no cloning is essential. So both copy protection and secure leasing are some functionalities that for which no cloning term is essential. And classical information is not useful for achieving that, and quantum information is essential for achieving them. In recent years, there have been several works that considered copy protection and secure leasing for cryptographic functionality. And especially, we focus on public key encryption and digital signatures, which are one of the most important cryptographic functionality. And for public encryption, there are already both copy protection and secure leasing. On the other hand, for digital signatures, even though there is some research that studied copy protection, but there no research studied a secure leasing for digital signatures. So the natural question is the following: can we do secure leasing for digital signatures? In this work, we answered the question affirmatively. So we constructed two types of secure leasing for digital signatures. The first one is called digital signatures with revocable signing keys, or DSR key for short. In DSR key, signing keys can be securely leased. And after the leasing period expires, signing keys can be deleted. And the deletion of signing key can be regarded as a revocation of signing ability. And this is why we call it digital signature with revocable signing keys. And we construct such a signature scheme with revocation capability of signing key, a Bayesian quantum hardness of learning with error problem, which is the basis of post-quantum crypto. And this is regarded as a very standard assumption in cryptography. And our second construction is called digital signatures with revocable signing keys, or DSR sign for short. In DSR sign, what can be securely leased is the signatures instead of signing keys. And we construct it based on one functions, which is even more standard assumption in cryptography. Here, let me make some comparison between copy protection and secure leasing. So in general, copy protection and secure leasing are incomparable functionality. On the other hand, in most cases, a copy protection is much harder to achieve than a secure leasing. And in most construction of copy protection, we can easily modify that to achieve secure leasing. So in this sense, copy protection is somehow stronger functionality. So from this perspective, let's compare existing and our work. So in the previous work, there was the copy protection of signing keys. On the other hand, we achieved secure leasing of signing keys. So what we achieved is a little bit weaker than what is achieved by the previous work. On the other hand, the previous work relied on a very strong assumption of indistinguishability of obfuscation and one function. And especially so, indistinguishability of obfuscation is regarded as a very, very, very strong assumption in cryptography. On the other hand, our construction just relied on LW assumption, which is a very standard assumption, and that is even used in a practical post-quantum crypto system. So in terms of security or assumption, ours relied on much more reliable assumption. So here's a trade-off between what we achieved and the assumption. And this is about the comparison of DSR key. And for our second construction, DSR sign, we are not aware of any previous work that considered copy protection version of it. And so we believe ours is the first to consider the unclonability for signatures. Okay, so from now, I would like to explain a little bit more detail of our constructions. So first, I would like to explain what are digital signatures. In digital signatures, a signer first generates a pair of two keys, verification key and signing key. And the verification key is made public, and so this is available to everyone. On the other hand, the signer keeps signing key a secret, and this is not given to the other people. And when the signer wants to generate a signature on some message M, the signer uses the signing key to generate a signature on the message. And then this signature can be verified by using verification key by everyone. So this is the functionality of digital signatures. So what is the security of digital signatures? Suppose that there is an adversary, and the adversary can see the verification key because that is public, but it cannot see the signing key. And additionally, adversary can see many pairs of messages signatures. And then the adversary tries to generate a new pair of signature and message, such that the new message doesn't belong to the set of messages on which the signature is already generated. So the security says that adversary cannot do that. And so this is the security of digital signatures. Okay, from now I will explain our definition and construction of the DSR key, where we securely lease signing keys. So in DSR key, the protocol works as follows. The company wants to lease some signing key to the user, and so it encodes the signing key into some quantum state. Then the user downloads it to the local device, and then this signing key can be used to generate a signature on any message. And after generating some signatures, because the signing key is content, so the state of the signing key may change from the original state, but we require that the state after signing should be still usable for further signing. So this signing key can be used to generate many signatures on many messages, as many as she wants. And at some point, the company wants to request her to delete the signing key. At this point, then the user deletes the signing key and generates a proof of deletion. Then by using some private verification key for the deletion, the company checks if this is very a valid deletion proof or not. And if it passes the verification, this ensures that the signer no longer has the ability to generate further signatures. So this is what we want to achieve by the DSR key. And we construct the DSR key from LWE by going through another type of signature, which we call two-tier one-shot signatures, or 2OSS for short. So in 2OSS, there is a set of algorithms that generates two parameters, public parameter and secret parameter. And public parameter is of course made public, but secret parameter is hidden. And by using public parameter, everyone can generate a pair of quantum signing key and classical verification key. And the message space of 2OSS is 1 bit. And when message equal to 0, we can generate a signing key to generate a signature on 0. And the signature on 0 can be verified by using the public verification key. So this is just a normal signature. And when the message equal to 1, we can also use signing key to generate a signature on 1. But what is different from the normal signature and also normal one-shot signatures is that for verifying a signature on 1, we need the secret parameter, which is not known to the public. So only the authority who knows the secret parameter can verify the signature on 1. So, okay, so this is a functionality of 2OSS. And as a security, we require the following. One cannot generate signatures on both 0 and 1 simultaneously. So as I said, a signing key can be used to generate either a signature on 0 or signature 1, but one cannot generate both of them simultaneously. And this is security, and more precisely, this holds when secret parameter is not given to the adversary, even if verification key is generated by the adversary. So this is the security of two-tier one-shot signatures, or 2OSS. And we observe that 2OSS can be constructed from LWE based on existing work by Okinawa et al. So we can just use it. So from now, I explain how to construct the DSR key from 2OSS. And the idea is to use a classical construction called Lamport signatures and instantiate it using 2OSS instead of one function. So how does it work? The signing key of our DSR key consists of a pair of signing keys of 2OSS. And we label each of the signing key by bit 0 and 1. And so for signing a message, 1-bit message M, the signer uses the signing key corresponding to M to sign on 0. Here, remark that regardless of the value of M, it signs on 0 instead of M. So this is a little bit confusing part, but the reason will become clear soon. For example, when she wants to sign M equal 1, it uses a signing key for the bit 1 to sign on 0. And if you remember the definition of 2OSS, the signature on 0 can be publicly verifiable. And the reason why we need to sign on there is to make sure that the signature should be verified publicly. And it is easy to show that this satisfies the one-time security as a normal data signature, meaning that when adversary gets only one signature, it cannot generate further signatures. Because intuitively, when adversary is given only signature on one, then no information of the signing key for there is used. So it is not very useful for generating the signature on one, for there. And for deletion of the signing key. So, okay, so suppose that after generating the signature on one, she wants to delete the remaining signing key, then she uses the remaining key to sign on one. And the signature on one of the two OSS is regarded as a proof of deletion. And if you remember the definition of two OSS, for verifying the signature on one, we need some secret parameter. But this is fine because in our definition of DSR key, we allow the company to use the private information to verify the proof of deletion. So this is consistent to our definition of DSR key. And why is this secure DSR key? And actually, this is a consequence of the security of 2FF. And security of 2FF says that you cannot generate a signature on 0 and 1 simultaneously, but proof of deletion is a signature on 1, and the signature of DSR key is a signature on 0 of 2FF. So by the direct reduction to the security of 2FF, once you generate a deletion proof, you can no longer generate a proof signature for the corresponding position or corresponding bit. But this is actually not a full construction because there are still two problems. The first problem is that it only supports 1-bit messages. And the second is that it is only one-time secure. And so we have to overcome these issues. And actually, we overcome these two issues by using analogs of some classical techniques. So let me start from the first one. From 1-bit to multi-bit messages, we use bit-by-bit signing and then hash and sign. So let me explain this by using a picture. So suppose that you want to sign a message M, then you first use some hash function to hash this into some small digest H of M. Then you sign on each bit of H of M. And in this way, you can expand the message space while preserving the one-time security. And then, so the first problem is easily resolved by this idea. And for the second problem of strengthening one-time security to maintain security, again, the idea is inspired by classical analog. So essentially, the idea is the following. Whenever signing on a new message, we generate a fresh new key pair and then sign on the message concatenated with the new verification key. And then each signing key is used only once, so we can reduce many-time security to one-time security. So what does it mean? So suppose that you have a key pair, verification key, and signing key, and you want to sign in this message. Then you generate a fresh key pair of verification key or signing key, and you use the old signing key to sign in the concatenation of the message and the verification key. And at this point, the new verification key is certified by the old signing key, so it can use the new signing key for the further signing. And in this way, we can make sure that each signing key is used only once, and this is why we can reduce mean-time security to one-time security. And this is finish the explanation of DSR key. And next, I will briefly explain the DSR sign, which is our second construction. So in DSR sign, what is leased is the signatures. So when the user downloads signatures, everyone can verify the signature. And when it is deleted, she can issue some proof of deletion. And after issuing the proof of deletion, she no longer has a valid signatures. And this is DSR sign. Okay, so this is proof of deletion is verified by some private verification key. And unfortunately, I don't have a time to explain the detail of the construction of DSR sign, but we constructed it from one function. And I just sketched the construction. And our construction is based on the intermediate tool, which we call two-tier tokenized signatures, or 2TS for short. And this is very similar to 2OSS, but the difference is that the security is required only when the verification key is honestly generated. And if you're familiar with the relevant literatures, this relationship between 2TS and 2OSS is very similar to the relationship between the normal tokenized signature and one-shot signature. And we construct 2TS from one function inspired by the recent work about public verifiable deletion. And yeah, the construction sketch here, and I don't have time to explain, but if you're familiar with the work, probably this sketch may make sense to you, I hope. And we construct the SR sign from 2TS. And the idea is to use the signing key of 2TS as a signature of the SR sign. And because the signing key of 2TS has some unclonable property, and this is inherited to our signature of the construction, and this is why signature has some nice property of the security. And so this is the idea. Okay, let me summarize my talk. We constructed two types of secure leasing for a digital signature. The one is DSR key, where signing keys can be leased. And this is based on LW assumption. And the second is a DSR sign where signatures can be leased. And this is based on one functions. And as intermediate truth for constructing them, we introduced two-tier one-shot signatures and two-tier tokenized signatures, which is a weaker variant of one-shot signature and tokenized signature from standard assumption, like LWE and one functions. So this is the end of my talk. Thank you for your attention.
So we have time for questions. So there's one question. Over there. Yeah, okay.
Okay, so thanks for the nice talk. So I'm wondering, are there any implementation of publicly verifiable certified deletion of signatures or?
Okay, thanks for the question. So let me see. I think for example, if we require public verifiability, I guess that imply a public key quantum money. And the only known constructions of public key quantum money from some assumption is based on IO. So I believe we need to rely on IO if we want to achieve public verifiability.
Okay, thank you.
Any more question? Okay, so let's maybe thank Takashi again.
This is you. Yep. Okay, good. This to your belt.
All right.
Okay, so I guess we need to wait for 2 minutes
Sure.
so that for synchronization of the sessions. So let's wait a bit.
you say? Interesting.
Okay, so let's start the second talk. So the title of the second talk is Secret Sharing with Certifiable Deletion by James and Justin. And Justin will give a talk.
Thank you for the introduction. So let's imagine a scenario where you have some large pile of data and you want to store it, but you don't want to store it yourself because buying your own servers is expensive. There are a variety of storage providers that you could rent their storage. But the issue is you don't know who's trustworthy and who might try and steal your data. The classical solution to this is to use secret sharing, where you split your secret and you distribute your data over a variety of servers. Then, as long as not too many servers are trying to steal your data, you get security. And the nice part about secret sharing as compared to, say, encryption is that it doesn't rely on any computational hardness assumptions. So we saw during the earlier in the week during 2 of the invited talks that hardness assumptions can be nice, but they are assumptions. We don't know. Sorry, this is auto running. We don't know if they're actually true or if they're broken. But the thing about secret sharing is there is one assumption that is being made, and that's that the adversary doesn't corrupt too many shares. And in a world where data breaches are frequent, it's not necessarily true, or it's not clear how realistic of an assumption this is. Over long periods of time, the adversary could potentially steal extra shares. And as soon as one extra share is stolen here, we see that there are a total, if any 3 shares can reconstruct, the adversary we lose security completely, and the adversary is able to steal our data. So the question that we set out to answer is, can we hope to achieve security against an adversary who can eventually corrupt an authorized set of shares, something that's able to natively reconstruct? Now, in the classical setting, there's not really much hope because classical shares can always be compromised or copied. So there's no way of giving out a share temporarily or anything. But in the quantum setting, Broadbent and Islam showed that quantum mechanics enables certifiable deletion of secret information. And in fact, they and some follow-up work by Bartusek and Khurana considered a very limited notion of secret sharing with certified deletion, where there are 2 shares and you need both to reconstruct the secret. Let me be a little bit more specific about what I mean by secret sharing with certified deletion. Here, we split a classical secret into quantum shares. Then it's possible to perform a destructive measurement on a share to delete the information that it contains. Now, when a client wants to cancel their subscription at some company because maybe they're worried about their information security practices, or they just don't like the most recent price hike, they can ask the storage company to delete their information and verify that the information is actually deleted. So even if there is a data breach on this company, there's no issues. In this work, we have 3 main contributions. The first is definitions of secret sharing with certified deletion. The second is constructions. And the third is a new tool that we use to build our constructions and do the analysis, which is a high-rate randomness extractor for certain quantum entropy sources. For the rest of the talk, I'm going to start by giving our definitions. We actually have 2 different incomparable definitions: no signaling certified deletion and adaptive certified deletion. Then I'll go over the more technically interesting of the two constructions, which is for adaptive certified deletion, and give a security intuition of it. Finally, I'll give an overview of our high-rate seedless randomness extractors and conclude with some open problems. To figure out a good definition, let's start by recalling the definition for encryption with certified deletion. Here, the adversary starts with a ciphertext, a quantum ciphertext, and then it deletes it by producing some valid certificate. Finally, it gets the key and tries to guess the message. And it should not be able to do this, even if it's also given unbounded computational power at this step. Let's see if we can adapt this to the secret sharing setting. Imagine that we split our secret into some number of shares, let's say 7 shares, and any 5 of them are authorized and can come together to reconstruct the secret. Here, the left side of the wall is similar to the ciphertext, and the right side, which is inaccessible to the adversary, is similar to the key. The adversary deletes some of these shares that it has access to by producing valid certificates, and if it deletes enough, then the wall comes down and it gets access to the rest of the shares. This is a very natural extension of encryption with certified deletion, but it's not meaningful for all access structures. For example, what if the rest of the shares already form an authorized set? Then it doesn't really matter what the adversary did with the initial shares, because as soon as it gets the new shares, it already learns the secret. To deal with this, we introduced 2 different definitions of certified deletion for secret sharing, which capture slightly different adversaries. No signaling is a sort of fast but distributed adversary, whereas adaptive is a slow but more linear adversary. And I would like to mention that these 2 definitions are incomparable. Let's start off with the definition for no signaling certified deletion. First, we start off by splitting our shares. Let's say that we have 6 shares and any 3 of them are authorized. Now, the adversary gets to partition these shares into unauthorized sets. So there can be, in this case, at most 2 in each set. And they operate on each of these sets in a local manner. So there's no communication across these sets, and they must produce deletion certificates. They are allowed to share entanglement, though, across sets. Then, if they've deleted enough shares that the remaining shares, for example, here there are only 2, the remaining shares are unauthorized, then the adversaries get to combine their views. And for security, we require that the combined view should be independent of the secret. So it doesn't matter if you started off with secret 0 or secret 1, the final combined view is independent. Our first result is that there exists secret sharing with no signaling certified deletion for any monotone access structure. Here, S is an access structure is a set of authorized sets, and monotone just means that if you contain an authorized set, then you are also authorized. Now let's move on to adaptive certified deletion, the slower adversary. We start with the same split as before, except now the adversary does not get to see any of the shares yet. One at a time, the adversary can do 2 things. It can corrupt a share of its choice, or it can delete a share by giving out the certificate. If the certificate is invalid, then the experiment immediately aborts. It can keep doing this for as long as it likes. And the only constraint is that the set of shares which is corrupted but not yet deleted cannot be authorized. In this example, if the adversary controls 2 non-deleted shares, then if it gets a 3rd one, it just gets the secret. So the next step that it has to do, or that it's allowed to do, is to delete. And this experiment keeps going until the adversary eventually gets the opportunity to corrupt every single share. Then our requirement, similar to the previous case, is that the final view of the adversary is indistinguishable or is independent of the secret. So it doesn't matter if you start with S0 or S1. Our second result is that there exists a threshold secret sharing scheme with adaptive certified deletion security. And I'd like to mention that as an optimization, we can actually prepare the shares using single qubit operations. There's no entanglement needed. And a threshold scheme is just the running example I've been using, where you have some number of shares, let's say n, and then any k of them are authorized. Now let's discuss the construction. And I'll note that our construction is specific to threshold access structures, as I mentioned. Let's start by recalling prior work. They considered a scheme where you start with a classical secret and you split it into a quantum share and a classical share. If the adversary gets access to the quantum share and then deletes it, and then they get access to the classical share, then they cannot tell what secret you started with. I'd like to mention that only the quantum share can be deleted. The classical share is classical information. It can never be deleted. So let's think about it. Can we use this 2 of 2 sharing scheme as a black box? And actually, our no signaling construction does do this. But if we're going to try and adapt this to the adaptive setting, it doesn't quite work out. And the issue intuitively is that the classical share can never be deleted. So over a long period of time, as the adversary corrupts more and more shares, it eventually accumulates lots of information that it can use to subvert later deletions. And actually, there is an explicit attack in the adaptive setting on our no signaling construction. Let's dive into the 2 out of 2 construction slightly more and see why it needs this classical part. In their scheme, the quantum share contains some data qubits, which encode the secret, and some check positions, which are independent of the secret. You can think of the data positions as being in the computational basis and the check positions as being in the Fourier basis. If you were to know exactly where the data positions were, then you could simply measure them all in the computational basis and extract the data. Of course, this requires knowing where the data positions are, and so the classical share contains a mapping of where the data positions are and where the check positions are. Now, the issue here is that we need this mapping in order to decode the secret, but it can't ever be deleted because it's classical. So this gives us a little bit of a circularity where if we can protect this mapping theta, then we can get secret sharing with adaptive certified deletion. However, to get secret sharing with adaptive certified deletion, we kind of need to protect theta in the first place. So we're stuck. And our key idea is to use an approach where we can reconstruct without knowledge of the data indices. Our approach is based on Shamir's polynomial secret sharing, which turns out to have very good error correction properties. Let me describe that in a bit more detail. We're going to start off with a polynomial, f, where f of 0 equals s, our secret. And each share will contain some number t of evaluations of f. Mixed in with these evaluations are going to be some random Fourier base elements, which are going to act as the check positions. Now, as I'm sure you are all aware, if you accidentally measure a position in the wrong basis, you completely destroy the information. And this holds for both bases. Okay, so if we want the adversary to delete the information, we simply ask them to measure everything in the Fourier basis. And because it doesn't know which positions are which, the best it can do is just to measure almost everything in the Fourier basis. And whatever the measurement result is, gives us the certificate. So we can simply check each of the check positions and compare them to what the actual value in the Fourier basis should be. Okay, let's talk about, that's deletion. Let's talk about reconstruction. When reconstructing, we have a large number of evaluations of F that are mixed with some check positions that are uncorrelated with F. If we were to measure everything in the computational basis, then each of these check positions gives you a random error. Now, the key insight is that if we have enough redundancy, enough evaluations of the polynomial in k shares, then we can actually correct each of these errors. And so we actually show that it's possible to tune the degree of the polynomial, the number of evaluations in each share, and the number of check positions so that k-1 shares, which are unauthorized, doesn't reveal the polynomial. But if you have an authorized set of shares, at least k of them, then you can actually correct all of the errors in them. Now let's talk about the security intuition. So first, let's do a slight change of perspective. We're going to lazily construct the shares instead of constructing everything at the beginning of the experiment. So first, because the first D point, which consists of a little bit over 2 shares worth of information here, if we're looking at any 3 shares are authorized, because these first 2 shares and a little bit of the third one don't yet determine the polynomial, we can simply sample them uniformly at random, and then when the adversary asks to corrupt them, we copy everything over. Then, the third share, before it corrupts a third share, the adversary has to delete a share. Now, the third share to be corrupted has some redundancy with the polynomial. And so we have to use polynomial interpolation to find it. We can just do that using the copies of the prior shares in the challenger's register. And we can keep doing this to find the rest of the shares for the rest of the experiment. Now at this change of perspective, I'd like to go back and argue that the next share looks random. This is clearly true for the first 2 and a little bit shares, because these shares are actually truly random. Next, we can actually show that when the adversary deletes a share, which it has to do before it receives the third share, the challenger's copy, the actual share, becomes high entropy in the adversary's view. Then we show that polynomial interpolation acts as a good randomness extractor for this source of randomness. Speaking of randomness extractors, let's talk about our final contribution, which is a high rate unseeded randomness extractor. So here we have some quantum entropy source, which we run through the extractor and hopefully get some truly random output. And the input size and the output size can be different. Let's imagine first that if the source were a Fourier basis element, then we could just measure it in the computational basis and get true randomness. Easy. Unfortunately, that's not always the case. What happens if it's almost a Fourier basis state? And I don't mean in a geometrical sense. I mean specifically that this is a superposition of Fourier basis elements that are kind of close to just one of them. So you can imagine that the later half of the state is actually a Fourier basis element, and maybe the first few qubits are in the computational basis. In this case, it's not really clear that you get something truly random when you do a computational basis measurement. And additionally, the adversary might even have some side information about what these offsets are. So for example, it might know which positions are on the computational basis, and which positions are on the Hadamard basis. The way our extractor works is it simply measures everything in the computational basis and then applies a matrix R to the measurement result. And this gives you your output. We show that if every little m columns of R are linearly independent, then Rx is truly random, even given the side information register. An alternative view of this is that R should be a parity check matrix for a linear error correcting code with distance little m. Finally, I'd like to end with a few open questions. First, can we get adaptive certified deletion for general access structures? We only constructed this for threshold access structures. Next, what about a stronger definition and construction that captures both distributed and adaptive attacks? There's also the question of public verification. It's been pointed out to us a few times that our no signaling construction actually can be generalized to have public verification, since it's simply a black box compiler and it preserves public verification. But these techniques don't seem compatible with our adaptive construction. Another very interesting question is, what about other threshold primitives, such as threshold signatures, where you give out a variety of shares of a signing key, and together those shares can all come together to sign some message non-interactively. Can we enable a scenario where you give out your shares of the signing key, and then when somebody is kicked off the board of trustees, you ask them to return their signing key and they can no longer help sign things? Finally, there's also the question of high rate commitments with certified deletion. With our new high rate randomness extractor, it's very natural to wonder if you can just immediately or somehow use it to construct high rate commitments, or maybe high rate FHE, these other interesting primitives that need computational security with certified deletion. Unfortunately, there's some technical issues in just immediately adapting the construction and the analysis. So our high rate extractor is not quite enough. Thanks for listening.
Okay, so we also have plenty of time for questions.
Sorry if I missed this during your talk, but so for the no signaling security definition that you use, there's no notion of an extractor like part of the proof that you need for it to work. Is that correct?
No, it's all black box in prior works.
Oh, okay. And for this new extractor result that you constructed, it seems a little bit tailored to this adaptive setup, and you constructed it in a seedless fashion. Is it critical that it's seedless, or can you patch things over with a seeded extractor somehow?
Yeah, it actually is very important that it's seedless. And this comes up in several other works in certified deletion. The issue is if the adversary can figure out or has some, maybe even computationally hidden information about the seed, then it can influence the randomness source when it's doing deletion, and security immediately breaks. So if we could hide the seed, then this is fine. But hiding the seed gets us back to this circularity where in order to hide the seed, we need adaptive security already.
And I guess in some sense, a similar sort of problem might show up in the commitment setting.
Yeah, exactly. So prior work by Bartusek and Karana did use a seedless extractor there, but their seedless extractor is based on XOR and actually uses a very large source of entropy, say lambda bits, and then compresses it down to just a single bit of randomness.
Ah, okay.
Whereas here, we actually need to take almost a full share of randomness and then produce almost a full share of randomness.
I see. And so from this perspective, also an entropic uncertainty relation argument, like in the original broadband Islam, is not very relevant here, I suppose.
Yeah, for them, that was fine because, again, you can hide the seed and it only becomes revealed later. But again, you need to be able to hide the seed information theoretically for that to
Okay.
work.
Thank you.
Yeah.
We still have time, so good.
So I think there is some work that studied unclonable secret sharing. And could you give some brief comparison with that?
Yeah, so if I recall correctly, the unclonable secret sharing work actually ran into a lot of hurdles. And one of their main results is that you simply can't do it in some settings. Whereas in the certified deletion case, we actually are able to do it with no assumptions, no additional settings beyond the plain model. Yeah, I forget the details of their construction and their definition though.
So can you compare these definitions, like so one imply the other, or are they incomparable?
I don't recall right now. I think the definitions were incomparable, but I'd have to look at it again and get back to you.
Okay, thanks.
Okay, so are there more questions? Okay, if not, let's send Justin again.
It's okay.
Okay. When did you vote? Oh, okay. So
Should be called new.
this one. Just can you put the shares?
Okay, so the title of the third talk is Content Delegation with an off-the-shelf device by an author and Yuming, and Yuming will give the talk.
Thanks for the introduction and thanks all for coming. In 2077, large-scale fault-tolerant computers have reality with the effort of our audience. Okay. Okay. So with the effort of our audience, which is very important, we have these larger scale fault-tolerant computers, but they are still very expensive and requires extreme working environments like high temperature. It's unlikely you will purchase your own quantum computers or quantum laptop. So you want to delegate your quantum algorithms or quantum circuit to some cloud quantum computing company. So in such a scenario, the client sends the classical description of their circuit as well as the input to the quantum computing company and receive the measurement outcomes. In such a cloud computing scenario, both the client and the server have their own concerns. For client, they should not blindly trust the server. They should always ask whether this results are correct or not. However, the client has only a daily use laptop. They cannot predict the results with the predicts the result with the predictions. Okay. So even the result is correct, how do you know this quantum computing company was performing some quantum computers rather than using a supercomputer? For the server want to make sure this interaction is zero knowledge in the sense that the client only learns the correctness of the result without any other information. So for the purpose of, for example, prevent reverse engineering or against or protect IP. So our goal is to have a zero knowledge verifiable delegation of quantum computations. Several models have been proposed to achieve this goal. Each of them have some advantages and encounters some challenges. For example, in some models, we do not assume the client is completely classical. They have some limited but trusted quantum functionality, like quantum measurements or state preparation. However, in this case, the client is not so-called fully device independent. How do you know your quantum device is always trustworthy? Some other protocols assume the server is computationally bounded, and they use crypto techniques to against malicious quantum servers or quantum provers. However, in this case, we make some computational assumptions which haven't to be proved to be true, and a more powerful quantum server may be able to cheat. There are also some other protocols based on non-local games, which assume you have multiple isolated quantum servers, and they use the self-testing techniques to verify the quantum servers, they perform the desired quantum computations. However, in this case, you require many servers for the zero knowledge. It was shown by William Yuan and Slofstra that you need 6 servers, and it was recently proved by Kevin Mestel and William Slofstra that you only need 2, but still you need multiple servers. So to tackle all those issues, we propose a model we call the OTS model. In such a model, a single quantum server do the bulk of computations. And the client has an untrusted off-the-shelf measurement device, and we only require 1 round of interaction. Here, off-the-shelf refers to the fact that this measurement device is entangled with the server, but it does not depend on the computation instance. It only depends on the size of the instance. And this measurement device is also very small. You can imagine it only has log n buttons, which can specify constantly many qubits you want to measure. And we do not assume this measurement device is trusted. Instead, we develop new self-tests to verify that the server and the off-the-shelf device, they share the enough entanglement and they can perform commanded quantum measurements. Okay, so let me give you an overview. Suppose now you have a quantum algorithm which can track typhoon, which is your circuit C, and you want to know whether your set day flight will be affected. This is your instant X. And you want to delegate this computation task to IBM, let's say. So in the setup phase, you first purchase this off-the-shelf device from the server based on your needs, based on the size of the computation. In the first step, you do this circuit to Hamiltonian construction, and you send the classical description of this Hamiltonian to the server. Then server builds actual quantum systems and compute the ground energy and ground state and teleport the ground state through the shared EPR pairs within the off-the-shelf device and the quantum server. Then the client presses some buttons on the off-the-shelf device. Based on the teleportation keys from the server and the measurement statistics from the client, they can estimate the ground energy of this Hamiltonian. And the ground energy is low if and only if this is an accepting instance. Okay, so here this is just an overview, and I will refer to the step 3 as the energy test or the computation run of this protocol. Of course, this is not enough to verify the computation. We actually need to incorporate a test run with the computation run. So the trick is, with some probability, you will conduct the computation run. With some probability, you will add a test run. Importantly, the computation run and test run are distinguishable to the off-the-shelf device. And if your off-the-shelf device is functional and your quantum server is honest, then they can pass. So this is the necessary and efficient condition to pass the test run. Then you can claim that the output of the computation run must be correct. So you know they are doing the commanded things. However, if the off-the-shelf device and the server, they cannot pass the test run, then you know either the off-the-shelf device is broken or the server is malicious. Now, and so you can detect the malicious behavior. So now our task boils down to design the protocol that, based on the measurement statistics, verify that the off-the-shelf device it indeed faithfully performs commanded measurements, and it shares an adequate amount of EPR pairs with the quantum server. Let me first give you a toy example. In this well-known CHSH game, there are 2 players. Each receive a bit and output a bit. They win this game if and only if A plus B, the output, is equal to the XOR of the inputs. And the series sum shows that the maximum winning probability of this CHSH game is roughly 0.85. A cool thing is, if the 2 players can achieve this optimal value, then after some linear algebras, you would say the shared state must be an EPR pair, and the measurement operators performed by Alice and Bob, they must be poly operators, poly measurements. And so this phenomenon is known as the self-testing for a quantum system. This self-test is also robust in the sense that if you can only have the near optimal winning probability, you can still claim that your state must be very close to an EPR pair, and your measurement operators are essentially poly operators. So the punchline is, during the CHSH game, if you observe that the 2 players win the game, then you would have high statistical confidence to claim that they do share an EPR pair and they can perform commanded poly measurements. Of course, this CHSH only self-tests one EPR pair and the poly measurements on 1 qubit. For our purpose, we need a self-test to certify high entanglements and maybe breeds of polys. So Natarajan and Vedic invented a nice self-test called polybreeding test. This self-test can certify n EPR pairs by measuring all the n qubits. And based on this result, Alex Squillo has this brilliant idea of quantum delegation. So this is a 2-server scenario. So those 2 servers, they share EPR pairs. During the energy test, the computation run, one of the server teleports the ground state to the other server, and the other server measure the ground states. And based on the measurement statistics from the first server and the teleportation keys from the second server, the client can estimate the ground energy and know whether this is a yes instance or not. And they use this polybreeding test to certify you do have enough entanglement, and the first server, they perform the measurement operators correctly, and the second server, they perform the Bayer measurements for the teleportation. Intuitively speaking, in this scenario, the entire ground state has been teleported, and the client received many information. Here, they receive a poly-n bit answers, okay? And the teleportation keys, they are encoded in a poly-n bit string. So intuitively, it's very hard to make this protocol zero knowledge. Okay? Let me remind you, the intuition of zero knowledge is the server want to conceal their inner working. So to tackle this obstruction, we give a new energy test. In this energy test, the server only need to teleport a small portion of the ground state, indeed a constant many bit of the ground state. And to incorporate the test run and with the computational run, we gave a new self-test called low-weight polybreeding test. So in this self-test, the client only require the measurement device measure constantly many qubits. So the question length is log n and answer length is constant. And we show that this low-weight polybreeding test certifies an EPR pairs by only measuring constantly many qubits, 6 qubits indeed. Okay. And along the way, we prove a new version, an enhanced version of the well-known Gawasatami theorem to prove that this low-weight polybreeding test is indeed a robust self-testing. So the idea is the canonical optimal strategy for low-weight polybreeding test forms representation of poly group or Weyl-Heisenberg group, which is a finitely presented group. And any near optimal strategy, they satisfy all those relations in this group approximately. Gawasatami theorem tells you if you satisfy all those relations approximately, then you can find the exact representation nearby. So this exact representation is the thing you want to test. And for the purpose of zero knowledge, we use the techniques called simulatable codes given by Guilio, Yuan, Slofstra to show that in this energy test, because you only teleport a small amount of qubits, then it's very easy to simulate the reduced density matrix. Okay. Based on those technical contributions, we show that any polynomial time quantum computation, aka BQP, has a zero knowledge verifiable delegation protocol in the OTS model. So you can delegate all efficient quantum computation using this protocol. Here, if you think this off-the-shelf device as a separate quantum prover, then you can replace the BQP circuit with the QMA verification circuit. Then you can think this is an interactive proof system with two provers. By scaling up the techniques, we show that every language in QMA has a two-prover, one-round, zero-knowledge interactive proof system. If you were in Kieran's talk on Tuesday, you would know actually everything in MIP* has a two-prover, one-round, perfect zero-knowledge protocol. Compared to their results, the OTS interactive proof system is proof efficient in the sense that one of the prover is very elementary. It's just a measurement device and measure constantly many qubits. And the other one only needs a QMA witness for the completeness. So there are a few follow-up directions I'm interested in. First is you can think this off-the-shelf device as a complexity class. Okay? So it contains all the languages that can be determined by the off-the-shelf interactive proof system. And the question is, now we know QMA is contained in this class. What is the power of this class? Okay, so we conjecture that maybe this contains all NEXP. And the second direction is this proof of quantum knowledge. So this is an extension of zero knowledge. So this concept refers to the fact that the verifier, the client, they further has the knowledge of the fact that further becomes convinced of the fact that the prover, the server, has the knowledge of an accepting instance. We think by modifying the self-testing part, we can make OTS also satisfy this proof of quantum knowledge property. Another one is, can we find some new self-tests, which is very efficient, meaning that you have a log n bit question, constant bit answer, and achieve a high robustness, maybe a constant robustness, which is independent of the number of EPR pairs you want to test, and this may lead to a proof of a game version of quantum PCP. Okay. Thank you.
Okay, other questions?
Thank you for the talk. You were mentioning about self-testing an EPR pair using just 6-qubit thing. Can you share more details on it and how robust is the procedure? Yeah, this one.
Yeah, so this is not the only one using like only constantly many measurements to certify n EPR pairs. Like if you do this so-called CHSH2 game, or so the basic idea is every time you just randomly select like maybe 2 qubits and play something close to CHSH. And you can show that this is a robust self-testing. However, the robustness is much worse than the polygrading test. You can only achieve like inverse of poly-n robustness.
Okay. And like, what is the significance of this low weight PGT in this scenario?
Okay, so as I mentioned, there are many self-tests that can achieve the same quantity, but this low weight polygrading test can be incorporated with this energy test. Okay. So the important thing is the off-the-shelf device cannot tell whether this is a test wrong or a computation wrong. Otherwise, they can cheat in computation wrong, but pretend to be honest in test wrong. And the significance of low-weight polygrading test here is it can be corroborated with the energy test.
Okay. Thank you so much.
Yeah, we have more time for questions. Benny.
Thank you for the nice talk. My question is, your protocol works by taking a quantum circuit, mapping it to a local Hamilton, and then delegating the computation. And I wonder, how is it if the computation is to be performed on quantum data? So, for example, assume that the user also has some other oracle that has some quantum thing that he somehow wants to get to the other side. Is there an extension of the protocol that can incorporate quantum inputs?
I think there are a few protocols that the client has the ability to, for example, measure or prepare some states.
Yeah, but then I mean, in the sense that the user has an unknown quantum data. So he cannot tell the server to prepare this or that state.
Well, I haven't thought about this,
Okay,
but that's a good question.
thanks a lot.
More question? Okay, so if not, let's thank all the speakers of the session again.